Okay. So today what I'm going to do is I'm going to finish the section. There's no new homework tonight, but did you get my email about, and I'm recording this. You got the email about if you didn't finish the homework, that's fine. And in general, if there's something on the homework that just doesn't look familiar at all, there's a difference between a small extension of concept and a new concept. It's okay to skip that and get back to it because I might get to it at the next lesson. The homework was created before we went over the lesson, so I thought that I'd have more time. I just didn't. So we're going to finish it today, and there won't be a new assignment tonight. Just finish the last assignment. So working on this, I want to talk about this problem first. This is page 6? Page 7, thank you. Page 7. Yeah, Chazzy?
I don't have a tablet.
Oh no, I should have found out during break. You're gonna have to just take notes for now, I'm sorry. Would it be a good idea to multiply through by x to get rid of that denominator?
What?
Would it be a good idea to multiply through by x just to get rid of that denominator?
Oh no, because you don't know what x is. So you don't know what x is.
Exactly, x would be positive or it could be negative, and with an inequality you have to be careful. If it's an equation, that'd be a great first step. But as an inequality, we're not going to do that. So instead I'm going to take that 7, move it over to the left. So we have x plus 12 over x minus 7 is less than 0. But now what? Common denominator. Under that x is a 1. Under the 7 is also a 1. The common denominator, of course, is going to be x. So let's make it happen. X over 1 is going to become x. Well, I'll just say times x on top and bottom. Times x on top and bottom here. So yeah, x squared. I'll put this in standard form. Minus 7x plus 12 is less than 0. Are we comfortable with that work like that? Okay. And the top of that fraction, of course, we're going to factor it. So x minus 4 and x minus 3 all over x. So shall we graph that thing on the left? If we know how to graph it, yeah, but you know how to graph that? Is that a parabola? No. We'll be graphing that towards the end of this chapter. So, but for right now, instead of graphing it, what we're going to do is linear analysis. What's that? Oh, nice. But I hope it makes sense that if there are three numbers for which if I plug it in, this side will have no sign. Like 4. If I plug in a 4, there won't be a sign, will there? Also a 3. If I plug in a 3, no sign. Also, I plug in the 0, this will have no sign on the left. But if I plug in any other number, the result will either be positive or negative, won't it? Okay, so that's when the line analysis comes in, or boundary algorithm. So on this line, I'm going to put the three numbers in order 0, 3, and 4. And now just test points. Like I like to go from left to right. I don't care which order you go in. Less than 0, I'm going to plug in negative 1. I don't care what the result is. I just care if it's positive or negative. When I plug it in negative 1 here, all I see in my mind is negative. I don't care about the negative 5. Negative times a negative over a negative. So the work that I'd want to see here is negative times a negative over a negative, which results in what kind of a number? A negative number. Does that make sense? That works for any number I would plug in there. On this side, if I plug in a negative 5, negative, negative, negative. If you want to cancel out a couple of negatives, you want to make this a positive 5. The result is a negative. Next number I'm going to plug in would be 1 or 2. Those are good numbers to plug in. 2.5, another fine number, nothing wrong with that. If I plug in a 1, we're left with a negative times a negative over a positive this time, which results ultimately in a positive number. And what number should we plug in between 3 and 4? 3.5. Pi, 3.1. It doesn't matter. If you're looking for behavior, it shouldn't be difficult. 3.5, you have a negative times a positive over a positive. You see, it's much easier to plug in the factor form than try to plug in the 3.5 up here, the expanded form. Always plug it into the factored form. So I think what I said was 3.5 gives me negative times a positive over a positive, which results in a negative number. And then the number of greater than 4, let's plug in a billion. Is that greater than 4? I think so. It's a little slightly greater than 4. A billion minus 4 is 900. I don't care. It's positive times positive over positive. The result is all positive. At that point, once you've shown the work for 3.5, you're fine. Not showing the work for that one. I understand that you can do it, especially with huge numbers like that. So our answer?
Negative infinity, comma 0 is an open parenthesis.
Nice.
You need parentheses 3,
Yeah. This is called an open interval. They're both called open intervals when they're both parentheses on either side, as opposed to not open, but closed intervals with brackets. And the problem with open intervals is that it looks like it might be a coordinate. So how are we supposed to tell the difference between interval notation and coordinates? Context. Right? This union here is good context. If it's talking about a bunch of numbers, it's going to be interval notation. It's talking about a specific place, and that's a point. Make sense? Cool. Let's go on to some word problems, shall we? Oh yes. Throwback to Algebra 1, Algebra 2. Motorboat heads upstream a distance of 24 miles on a river whose current is running at 3 miles per hour. Who has seen a problem like this? Motion on a current. Okay. If you haven't, that's okay. We're going to go over exactly how to do these. The trip up and back takes a total of 6 hours. Oh, it takes a total of 6 hours. Assuming the motorboat maintains a constant speed throughout the trip, find that speed. Now, when I say the motorboat can maintain a constant speed, that means whoever's driving it keeps it on the same setting. So if it's in still water, it goes a certain amount, a certain speed. Of course, if it's going upstream, that speed is going to be decreased, won't it? By 3 in this case. And when it's going downstream, it's going to be increased. It's like walking on those moving sidewalks. Going with it, you feel like Superman. You're going super fast, but your normal speed has suddenly increased without any sort of extra effort. So I'm going to use one of these charts. Have you seen this before? What kind of chart is this called? Dirt. RTD chart. R times T equals D. If you haven't done these before, that's okay. This is a suggested way to do it. You're welcome to use another way if you'd like. There's upstream and downstream. Okay, so it has upstream a total of 24 miles on a river, so I could put that 24 here, and downstream also 24. What should I say about the rate? Yeah, so let's define a variable. Let x equal rate of boat in still water. In which case upstream is going to be x minus 3 and downstream is going to be x plus 3 because again it's going either faster or slower at that time, at that point.
Well, do you have to, like say, in the let x's, do you have to specify that
You don't have to. That'd be nice to do, but it's okay at this point. I'm relaxing this with that stuff. Now, time here, we don't know much about the time. You could introduce another variable, but I'm going to ask you not to introduce another variable, which means we're just going to use what we have here to fill in that time. And since we know that d equals r times t, we also know that t equals d over r. We have d, we have r, so this time I'm going to call 24 over x minus 3. This one I'm going to call 24 over x plus 3. Yes?
Well, we can also set y.
Yeah, y, then. x minus y. That's fine. But what's nice about this is that it brings it into this chapter. What would I do next from this information? Do you see what I would do from here? I have to make an equation. The only thing we haven't used is that whole 6. It went a total of 6 hours. Okay, well, upstream took this much time, downstream took this much time. You see the equation? We add them together to equal 6. To solve this, should I get a common denominator? You can, but remember for an equation, my recommendation is to eliminate the denominator. Just cancel by multiplying by that which would have been the denominator. In other words, going to multiply by x minus 3 and x plus 3. So that first term becomes 24 times x plus 3. The next one, 24 times x minus 3. And the other side, don't forget to do both sides. Do you mind if I just say x squared minus 9? Is that comfortable to multiply that on that side since it's already conjugates? So it just happens to be. Also, if you wanted to, it'd be nice to maybe divide it by 6 or 29. You guys don't have to do it. I'll give you a minute to finish this. Get it? Yeah. We're finding the speed. Did you get it? What'd you get? X equals 9? Which means it went downstream how fast? I'm sorry, downstream went 12 and upstream. It wasn't asking for that, but the constant speed that was set was 9. And let's put at least a unit on it. I'm being a little bit lazy here because I have a lot to go over with you, but you know that for a word problem, you should include a sentence answer. It travels 9 kilometers per hour, or miles per hour in still water. Yes? I hope that was comfortable. I have something for you. Please pass it back there. Review. For the 16. Right. Yeah, before we talk about Anna and Elsa, I want to talk to you about someone much more famous, John and Tim. Yeah, John and Tim. I don't have a song about them. On the paper I just gave you. There should be a John and Tim on this. So let's try this problem. Let's try 2 hours. 2 hours from John to travel 1 kilometer, Tim to travel 1 kilometer in 1.5 hours. They start at the same rate. And how long will it take John and Tim to travel 1 kilometer in total? So this seems familiar, but this is probably different from most of the RTD type of problems we've done. But I'm going to start the same. R times T equals D. And we have information for John and Tim. Okay, so there's going to be some surprises here. Like when it says 2 hours for John to travel 1 kilometer, I'm not going to put 2 for time and 1 for distance. I'm not going to do that. So the question's asking something else. They're traveling 1 kilometer in total. So I don't know what his distance is. I don't know what his distance is either. But I know that in the end, these two will equal. But add to one. So for right now, what I could say is, like, takes John, takes John 2 hours to travel 1 kilometer. What information can I glean from that? A rate. Does that make sense? It takes them 2 hours to travel 1 kilometer. And if you want to put it all together, D equals RT, rate equals distance over time. So we have a rate for John of 1/2 kilometer per hour. How about for Tim? His rate is 1 over 1.5 kilometers per hour. But you would never leave a fraction like that, would you? 2/3 instead. 2/3. Now, if they're starting at the same time, that means the time that they're both running is the same. We could call it X. I'm going to call it T. Whatever you do, in this case, when it's like this, I don't require you to define your variable because I can see that T is the time that John and Tim are working. I can see that. As opposed to the last one, I couldn't see that very clearly, so I defined that X variable. For distance, what should I say there? Exactly. I don't want a new variable, so I'm just going to put what I have and put them together to say 1/2 T, 2/3 T. You see the equation that's going to come from this? 1/2 T plus 2/3 T equals 1. Now notice, if just John is running, then his time will be, if just John is running, it'll be 2 miles, 2 hours, won't it? Yeah. And if just Tim is running, it's 1.5 hours. But they're running together. You want to see how it goes together. First step, don't get a common denominator. Multiply by 6. And kill the denominators. And we could do that because it's an equation. We'll multiply both sides by 6. 3t plus 4t equals, don't forget to contribute both sides. Okay. Can I just finish this off without showing any other work? I can. I guess the question is, can you? Only you can be the judge. You show as much as work as you need to make sure you're not having any questions. 6/7 of an hour. Should we change that to minutes? No. Should you be able to? You should be able to. I'm not going to require something like that. Maybe if it said 1/5, I'd say how many minutes is that? But 6/7, I'm not that mean. Usually. Happy? It's a word problem, of course. I'd expect a sentence answer. It would take them 6/7 of an hour to run 1 kilometer in total. That's really slow, isn't it? That's like super slow. That's like elderly puppy or something. What's it? Oh, good point. They're like, don't want to drop anything. Oh, you're right. I feel like I need to qualify their slowness. Okay, here's a problem that you've never seen anything like this before. It takes John 2 hours for John to mow the lawn. Tim can mow the same lawn in 1.5 hours. Never seen anything like this before. How will it take? How long will it take them working together to mow the lawn? Okay, maybe you've seen exactly this problem. We are going to do it exactly the same, but notice there's no distance. Instead, it's going to be rate times time equals the jobs done. Who's done a problem like this before? Like a jobs problem. If you haven't, that's fine. If you haven't, it looks like only a few of you did. If you know another way to do this, you may use it, but if you get it wrong, I can't have anything to say about it. Okay, so we have John and Tim. If it takes John 2 hours to mow a lawn, that means his rate of mowing a lawn is 1/2 lawns per hour. Right? Who knew? For Tim, his rate, somehow I just know it's 2/3 lawns per hour. Or 2 lawns per 3 hours. Does that make sense? 2 lawns per 3 hours? Right? If 1 lawn takes an hour and a half. 2 lawns per 3 hours. The time, since they're mowing together, It is the same. And the amount of the job that John does is 1/2 t. The amount of the job that Tim does is 2/3 t. And I can take these and add them together. Now, if the question were asking how long does it take to mow 2 lawns, then this would be equal to 2. If it's 5 lawns, assuming they're all the same size, it would be equal to 5. This is just a single lawn. Somehow I could just look at this and know that the answer is, oh, you're all like masters of mathematics. Incredible, at 6 hours. So let's make sure that this makes sense. Here's the lawn. Here is John with his lawnmower, and he's going like this. If he just does the whole lawn, how long would it take him? It'd take him 2 hours. Luckily, he has his buddy at the other side who's mowing the lawn. Also, the question is, when will they come together? So it's mowing at the same time. That's why the T's are the same. I hope it makes sense. It's going to take less than an hour. They're working together, so we'll finish fairly, definitely faster, each one individually. So that's just the idea of what's happening. Everyone happy? So far, so good? Ready to let it go? You know what I'm saying? On to Anna and Elsa. Anna and Elsa. Is it Anna? Is it Anna? Anna and Elsa. Oh my goodness, I am showing my ignorance. I know the song, but I forgot that her name was pronounced Anna. Thank you. They can build a snowman. In 1 hour and 12 minutes. I'm so sorry. I'm so sorry. So they can build a snowman together in 1 hour and 12 minutes. Anna is much slower than Elsa and would take an hour longer than Elsa if both decide to make the same snowman by themselves. How long did it take Anna by herself to build a snowman? Sophie, do you know that's what I did? No, I said it right.
I think it's because we spelled that. Or is it?
But thank you for trying to find an excuse for my ignorance. I appreciate it. You're so nice, Sophia. We're going to have RT, not D, because they're not running a distance, not traveling. They're doing a job. In this case, that job is building a snowman. I think I see some people who need to be separated. We have Anna up here. We have Elsa over here. Yeah, Anna. Not right. We have too much to do. But after class, if you like, I would love to hear. I'm sorry to dismiss that for now. Okay, they're working together for an hour and 12 minutes. Now, hour and 12 minutes, of course, no one's going to leave any number in math like this, hour and 12 minutes. Instead, you're going to change this to 1 1/5, or you could change it to all minutes if you want 72 minutes, but I think hours makes a little bit more sense. So for those who just are confused about where that came from, 12 out of 60 is 1/5. And mixed numbers in math, there's a time and place for it, but we're going to change that to 6/5. Where's that 6/5 going to go? That's time, right? That's how long it took both of them. So this is all information about both of them working. It took them both 6/5 of an hour. Okay. I need to introduce a variable. What's the variable I'm going to introduce? X. Let x equal. Now the question is asking how long does it take Anna by herself? So I'm going to set x equal to the time it takes Anna to build the snow person, we'll say. And I'm going to draw it just to get out of that. There you go. Okay, so if x is the rate it takes for Anna to build a snowman, what is the rate? Oh, sorry, the time it takes for Elsa. The time it takes for Elsa would be x, but just the time. Anna's time is x. Elsa is x minus 1, isn't it? She's faster. It takes her less time. Well, I would start with Elsa, but it's asking how long do you take Anna by herself. So I want that to be the variable. I made that mistake in log 3. Okay, so the rate for Anna Rate for Anna. Well, I could get it from here that rate is equal to the jobs over time. So the job is just building one snowman. And the time it takes her is X. For Elsa, that's going to be 1 over X minus 1. Do you see what comes next? We have one more thing to fill in. That J column. J is, I like to put the constant first, so I'm going to put 6/5 times 1 over X. Or I could do 6 over 5X if you want. 6/5 times, actually I'll do that, 6 over 5X. 6 over 5X, and this is going to be 6 over 5 times X minus 1. I'm not going to multiply that out, I like to have factors. What's the next step? This is so abstract, and you see what it is?
1 over X plus 1 over X minus 1 over
Did you that these two are equal to 6/5? That's 6/5 times 10. So I'm not sure if you add these together. Take a moment to discuss. What is the next step? We do have to take these jobs. This is the portion of the job Anna's done. This is the portion of the job that Elsa has done. You take them, try something equal to each other? No, you take these, add them together to be equal to 1. If they're building 2 snowmen, it would be equal to 2. So we have 6 over 5x plus 6 over 5x minus 1 equals 1. How should I solve this problem? Let's multiply everything by 5x and x minus 1. Go ahead. I'll do it too silently while you guys are working on it. While you all are working on it. Did I do that right? You got it? Yeah, that works. That's good. I'll organize my numbers into here. I'm looking for numbers that multiply to be 30 and have to be negative 17. Have I shown you this method for factoring trinomials like this? We'll break this up. You can use whatever method you like as long as it works. So I'm going to factor out that 5x, x minus 1, factor out that 2, sorry, x minus 3. Right minus 3, oh, good time, x minus 3, 5x minus 2. Yes, Andrew? Oh, the x thing? Yeah. The way to organize information, I've multiplied this first maximum to get 30. And then I'm going to put the middle one, yeah, to negative 17. These two numbers add together to this, multiply to this. So I separated into that was connected to it. If you're interested in talking more about that, I'm happy to share that with you later, another time. So are there 2 solutions? There could be 2, except the problem is if it takes Anna 2/5 I have an hour to make a snowman. That means we take Elsa negative 3/5 to make a snowman, which makes no sense. So it takes Anna three minutes? Hours, I think. Is it hours? Is that the? It's hours.
Why would the 2/5 be negative for us? Oh, my bad.
Yeah, that's a good question. Thank you. Okay, so there's a lot of information that could easily get away from you, but I find that with these RTD or the RTJ charts, it's really a nice way to help organize it. If you have another way you want to do it that works, you're welcome to use it. But if you have a way that always gets you the wrong answer, I urge you to stray away from that method. That's a pro tip for me to you. Any questions? Kira, Brianna, did you guys did you have a question? I think you're both very thoughtful. What can I do to help you? Why am I eliminating that? But this is x. Remember, x represents time to odd of those things. So we could say 2/5 is a fine number, but if that works, then it takes Elsa, x minus 1 always. And that just can't be. Thank you for asking. Okay, I hope that we're connecting dots. We have one more thing we need to talk about. Special kind of fraction called complex fractions. So the book, or not the book, but the packet introduces two ways to go over it. For reasons of one, I don't have time to show you both ways, and two, I hate the first way. I'm only going to show you the second way. But if you really want to know the first one, I'm happy to show you. It involves combining like terms, getting common denominator, and just dividing. Okay, so 1 over a minus 1 over x all over 1 over a squared minus 1 over x squared. This always works very, very quickly. I'm going to use the identity property of multiplication, which says I can multiply any fraction by, or any number by 1, and it maintains its identity. So I'm going to multiply the top of this fraction by something, multiply the bottom of the fraction, and magically all the little denominators will be gone. Like if I want to get rid of this a over here, I'm going to have to multiply top and bottom by a. Now I'm not talking about top and bottom, because I'm talking about top and bottom of the fraction by a. That leaves x, that also leaves an a here, and so I'm going to multiply by a squared and x squared. You see that would cancel everything? But let's try it. Multiply top and bottom by a squared x squared. Don't forget to use which property? Distributive property. So, but also identity property. We're using identity property of multiplication. So 1 over a times all that is just ax squared. This times this is a squared x on the bottom. This is x squared minus a squared. So we no longer have a complex fraction, which is great. And it's half the battle. But remember, anytime you have a fraction, it must be left in simplest form. So let's factor it and see if anything cancels. The top, how do I factor that? There's an a and an x, so yeah, I'll factor out an a and an x, leaving us with x minus a. The bottom, what 3 words should be running through your head? Difference of squares should bring happiness to your body and mind. Oh, look at that. Should I cancel the x's? Just the a's? I cancel the a's though, right? Why don't I cancel the x's or the a's? In addition, it's got to be factors. Only cancel factors. I should make a t-shirt and sell it. I swear, I think that it would take off. Thank you. Extra credit. So very quickly, this one. To do this, all you have to do is multiply top and bottom by 3n. And then the solution to all your problems will be revealed to you. Is there a guarantee that there's going to be a way to simplify it after this? No, but it won't be complex anymore. My beautiful people, have a great weekend. And for those of you who celebrate, have a happy new year. this off.
You already know.